Well, welcome everyone. Thank you for joining us today. First, I'd like to start with some introductions. I'm Colin McNaughton. I head up engineering at Neve Research. We're the creators of the X platform, which is a platform for building high-performance, simple-to-author applications, leveraging some of the tenets of in-memory computing. And I'll be co-presenting today with Igor. Igor, are you on? Do you want to introduce yourself?
Hello, my name is Igor Mihadjevic. I'm a lead engineer at Code41. We specialize in high-performance system design. We design custom software solutions for other clients. And this is also my professional focus. It's related to stream processing, big data processing, online gaming, ad bidding, targeted advertising.
Cool, thanks Igor. You'll be hearing more from him later. So today we're talking about streaming applications and specifically how to write streaming applications that are exactly once. So allowing applications to be written without having to worry about duplicate or dropped events in the event stream. So I'm going to start off by just talking about some of the challenges associated with doing exactly once streaming. Then I'm going to pass off to Igor, who's going to walk through a case study on writing an ad exchange, leveraging sort of exactly once streaming, which is built on top of the X platform. And then he's going to transition into a demo. So what are the characteristics of a streaming app? They're pretty simple, right? We have sort of a fire hose of inbound messages or events, and we want to do some processing on those, which involves updating some application state. And then as a result of that processing, we're going to send out a bunch of outbound messages that form their own stream. So the key sort of things we want in such an application is the ability to kind of stream without blocking, and we'd like these applications to be highly available. So, you know, if there's any sort of failure during that processing, or, you know, the application goes down, we're able to fail over to a backup instance to resume processing without interruption or loss or duplication. So pretty simple flow though, bunch of messages coming in, we process them, which updates some state, and we're going to emit outbound messages that make up their own streams. So the title of this presentation is Why Do Microseconds Matter? So the key thing to remember when working with streaming applications is that any sort of blocking operation you do, or any sort of processing you do, has a direct effect on the throughput that you can sustain for a stream of messages. So for example, a message processing time in your stream of 1 millisecond is going to limit your throughput to 1,000 messages per second. You know, there's only 1,000 milliseconds in a second. So that actually has several ramifications when working on streaming applications, because you're working with an ordered stream of messages, and so, you know, any kind of blocking ties up the next message that I can process. So we need sort of very high performance pipelining to do streaming applications. Now, when writing exactly once streaming applications, there are a few main challenges, and they fall into kind of 3 categories here. So one of the challenges is around the messaging piece. Any sort of synchronous messaging you do falls back into that prior category of something that could take time that's going to block your stream processing. Same goes for operating on your application state. If it takes me a millisecond to save a state change before I can process the next message, I'm effectively gating the throughput at which I can stream. And then the third one's a little bit more subtle, but it's how do you combine your messaging streams with your updates to state. So in an ideal world, while I'm processing a message, I want the inbound messages and events that I'm emitting to be consistent with my state. So we'll talk about these a bit more. So first off, the messaging challenges. So when I'm writing a streaming application, the events that are coming in over messaging. And if I want to do exactly once streaming, that implies that I'm going to have to acknowledge those messages to whoever's sending them to me. That way, if I fail, my process fails, the sender can resend those messages. And this leads to some complexity on the application's behalf, because as soon as you start doing that, acknowledgements can get lost. And I, as an application, need to be tolerant of some amount of duplication after a failover. And then beyond that, I touched on it before, but acknowledged messaging implies a synchronous operation. I send a message and I have to get an ACK. So what you need in a messaging provider is windowed acknowledgements, so that when I send a message, I don't have to wait for an ACK. I don't have to wait for the receiver to tell me that I got the message. So a couple, small kind of considerations that you need to keep in mind for your messaging stream processing. On the state side of things, if I receive a message in a stream, I need to make sure that the changes to my application state that I make are saved before I send any outbound messages, because if my process fails, I want to come back up, remembering those changes that I made to my application state. So some of the traditional application architectures don't lend themselves too well to streaming. If I'm saving to a database that's in another process, it's going to be far too slow to save and update in a database and wait for that to be synchronized to disk. Same holds true of data grids. They're a little bit better, but still slow. If I've got my application state sitting in a data grid somewhere and I need to save some sort of state change or access some state out over the network, that round trip time to save or read state is going to be a fundamental gate on the throughput and latency of my stream. So I could save locally my state to disk, but even on fast solid state drives these days, random access reads again will go up over a millisecond or more. And one disadvantage to saving to my local disk for the application is it doesn't give me a high availability mechanism in the event that my entire machine fails and I need to fail over to another machine. So one other small challenge with state is the amount of contention. If you have multiple threads or multiple processes that are both competing to update the same piece of state, that's also going to slow down your ability to process and operate on that state. And that tends to get worse if the state that you're contended on is sitting in another process like a database or even a data grid, because then the protocols that you're working on to moderate that state contention gets even more costly. And then the final challenge that I want to speak about today is maybe the most complicated piece of doing exactly once streaming, but it's the concept of I've got this stream of messages coming in, and I want the processing of that stream to be consistent, atomically consistent with the changes I make to state. So Igor is going to talk about this a bit later, but say in the ad exchange space, if I'm an ad exchange and I get a winning bid from a provider and I send that ad down to a user's browser, but then my process fails and I don't remember that I sent that message down to the browser, someone's going to end up getting charged when they shouldn't. So I really want those messages that I send outbound to the outside world to be consistent with the processing in the state that I'm remembering. So what kind of, how do we deal with the sort of difficulties that I talked through before? In Neve, in the X platform, we believe in a micro app architecture. Micro app architectures are like microservices, where an application has its own private state that sits entirely in memory. And that gets you away from some of the challenges we were talking about before, where you have data sitting in a data grid. When my state's in memory, I can operate on it immediately. We also need to do pipelined replication to a hot backup if we're going to move all of our memory into state. So in the X platform, we keep all of your application state in memory, and we're pipelining all of the state changes that your application is making to a backup, which is ready to take over in the event of a failure. On the messaging side, we use pipelined guaranteed messaging, and we, along with the state changes that we're replicating, replicate the pointers in that stream to which we're recursive. So on a failover, we're not going to process any messages in a duplicate fashion, nor will we lose any. And then the sort of secret sauce in the X platform is how we ensure that any message you process is 100% atomic with any state changes you make. So you can write application message handlers in a fashion where you can assume that any event's going to be processed once and only once, and that your state changes are 100% consistent with those messages that you're sending. So what does this look like in an X platform architecture? You have inbound messages streaming in, and they're going to be, you're going to operate on those messages. Any changes that your application makes to state will be replicated to a backup, and then that backup, once receiving it, will stream that acknowledgement back to the primary, which will release outbound messages. So what this entire flow gives you is a 100% non-blocking stream of messages flowing through the system, flowing through your application handlers in a 100% pipeline fashion. So, so essentially what we have here is an entirely non-blocking flow that operates, at very low latencies and can scale up to very high throughputs. So that's the X platform in a very high-level nutshell. I'm going to pass off to Igor, who's going to walk through how he's used the X platform to author an ad exchange.
Okay, thank you. As I mentioned at the beginning, most of the projects that we do are related to stream processing or targeted advertising or online gaming, and all of these are great candidates for message-driven development. So based on our past experiences with these kind of projects, we partnered up with Neve Research and to try to build a project that we built before to develop a new solution. And one of the projects that is also message-driven is ad serving online. So just to give you some introduction on how ad serving works. So on one side we have a user, a consumer, and on the other side we have a brand, some kind of company that wants to sell a product or a service, and they want to advertise it to a user. So the company may hire a marketing agency, and marketing agencies are the entities that design ad campaigns. They purchase TV airtime or billboards, or they purchase online ad space. So the way it works is that the user online is viewing some kind of content on a browser or on a smartphone device, and the content is a place where an ad can be displayed. The content is a web page or a video, and the browser will make a request when the user wants to view a page to retrieve some kind of content from a publisher. Publisher is a content provider, which can be a news website or a blog or a video clip site. And the process starts when user makes a request to content server to retrieve the page, and then page is returned with markup containing placeholders for where the ads will be displayed. So the first and the simplest case is when a publisher sells an ad space directly to some agency. For instance, an agency can make a deal with the website owner to purchase a certain ad space for a certain time, or for a certain number of clicks, for a certain number of impressions. And in this case, the browser was directed to publisher's content server, and the ad is retrieved and displayed in the browser. So if the publisher didn't sell its available ad space directly to anyone, the ad space will be, they can offer this available ad space on an open market to try to sell it to someone. And this is the interesting part that involves selling an ad space, and on the other side competing for it, bidding for it, and purchasing it, all happening in the real time while the page is being loaded to browser. So the publisher was sent the request to supply-side platform, which is a technology platform that provides certain services for the publishers. The way that they can organize their available ad space, they can sell it through SSP and receive some revenue for ads. So the supply-side platform will send an ad request to an ad exchange, and ad exchange is a platform that will auction this ad space, and then it will decide on the winner, on the best bid, and then this will be the one that will purchase the ad. So ad exchange will send a bid request to any interested bidder. The bidders are usually demand-side platform applications. The DSP is a platform that provides services to the agencies, to the ad buyers, the same way that the SSPs provide some services to the publishers. So the DSP will provide services to the agents, to marketing agency, to be able to create campaigns, to manage them, to track the efficiency, the conversion rates, and to see the actual effectiveness of a certain campaign. So this bid request is sent, and the response is expected to happen in about half the time that the whole ad request is needs to take. For the ad exchange, the constraint is around 100 milliseconds, and the constraint for anyone who is willing to bid is around 50 milliseconds. The demand-side platform can utilize the data management platform. This is like a data warehouse. It's a place where we can store some information about the users if they are being tracked, for instance, some info tied to the cookie. This can be users' interests, some demographic data about like gender or age, anything that can help us target them better for ads that are interesting to them. Now, the constraint of 50 milliseconds is something that if an ad exchange can respect this constraint, then the bidders can also be other ad exchanges. We can make a chain of requests, but every latter participant needs to follow much stricter time limits. So at some point, the ad will conclude the auction once everyone sends their offer, their bid, and then the winning bid will be determined, and this will be propagated all the way to the browser. So the browser now has the information how to retrieve the ad. It's usually a URL or a piece of markup code, and the browser will then retrieve it from the ad server. The ad server can be tied to DSP or ad agency, and it can be used any information that the ad server has about what the user did with the ad can then be used to further improve the campaign, to change the strategy to increase user conversion or to increase effectiveness of the campaign. So there we have it. This is how the real-time ad bidding works, and this is actually being standardized by the biggest businesses that are in the ad serving, and the institution is called IAB, and they have developed a standard protocol called OpenRTB. It's also worth mentioning that not all the components are always separate. Sometimes a business will integrate everything into a single offer so that both publishers and ad buyers would go to the same business to connect. So the publisher was sent the request to supply-side platform, which is a technology platform that provides certain services for the publishers. The way that they can organize their available ad space, they can sell it through SSP and receive some revenue for ads. So the supply-side platform will send an ad request to an ad exchange, and ad exchange is a platform that will auction this ad space, and then it will decide on the winner, on the best bid, and then this will be the one that will purchase the ad. So ad exchange will send a bid request to any interested bidder. The bidders are usually demand-side platform applications. The DSP is a platform that provides services to the agencies, to the ad buyers, the same way that the SSPs provide some services to the publishers. So the DSP will provide services to the agents, to marketing agency, to be able to create campaigns, to manage them, to track the efficiency, the conversion rates, and to see the actual effectiveness of a certain campaign. So this bid request is sent, and the response is expected to happen in about half the time that the whole ad request is needs to take. So for the ad exchange, the constraint is around 100 milliseconds, and the constraint for anyone who is willing to bid is around 50 milliseconds. The demand-side platform can utilize a data management platform. This is like a data warehouse. It's a place where we can store some information about the users if they are being tracked. For instance, some info tied to the cookie. This can be users' interests, some demographic data about like gender or age, anything that can help us target them better for ads that are interesting to them. Now, the constraint of 50 milliseconds is something that if an ad exchange can respect this constraint, then the bidders can also be other ad exchanges. We can make a chain of requests, but every latter participant needs to follow much stricter time limits. So at some point, the ad will conclude the auction. Once everyone sends their offer, their bid, and then the winning bid will be determined, and this will be propagated all the way to the browser. So the browser now has the information how to retrieve the ad. It's usually a URL or a piece of markup code, and the browser will then retrieve it from the ad server. The ad server can be tied to DSP or ad agency, and it can be used any information that the ad server has about what the user did with the ad can then be used to further improve the campaign, to change the strategy to increase user conversion or to increase effectiveness of the campaign. So there we have it. This is how the real-time ad bidding works, and this is actually being standardized by the biggest businesses that are in the ad serving, and the institution is called IAB, and they have developed a standard protocol called OpenRTB. It's also worth mentioning that not all the components are always separate. Sometimes the business will integrate everything into a single offer so that both publishers and ad buyers would go to the same business to connect. So we have developed several of ad serving systems, and some of the problems that we have encountered, one of them would be that we had to build everything from scratch. Once we have these very strict limits on the speed, then we have an issue that there is very little reusable code that's available to publicly available in open source community to build these kind of applications. So we usually had to build everything from scratch, from the network layer, from HTTP servers that had to be custom written all the way to storage, to everything else. So if we are handcrafting everything, then we do have a problem how to design for concurrency, how to scale, how to achieve reliability, because in custom solutions there is always a problem that there are so many moving parts that it's easy to introduce errors, especially since we are developing for startups. Teams are usually small, and the deadlines are short, and we usually had to hand over everything that we create because the client would have the copyright on the entire code. So if you are building a new system, there is no reuse of anything that we did. So the problem can also be the storage. Once we have optimized everything for speed, there is always a hog on the actually persisting the data. And we had always issues how to make a good persistence layer. Another issue is doing real-time computing on virtual machines. Garbage collection and real-time computing are not really going well together. So we have an issue with garbage collectors posing the VM or simply at some point spending CPU that blocks the actual business logic. And as you saw, the 100 milliseconds is a very strict constraint. So garbage collection pauses can cause data loss and they can cause money loss. We had a complicated kickoff of when we are setting up the project. Developers need to do a lot of configuration. For instance, if you want to use Apache Cassandra for storage, then you can do something with maybe one node, but you better have 3 nodes, so you would need the 3 machines and so on. So all of these components require a lot of configuration, and it's complicated for our IT guys in DevOps when we need to set this up for production. We need to set this up for deployment. There are many different components, and they need to manage all of them, and they need to do it on a lot of hardware. So we tried creating an ad serving system on the X platform, and these are our findings. So we have created an end-to-end product, a full product that involves everything from the DSP to SSP, and we use the efficient binary protocol. We connected all of these applications to the same message bus, and they were communicating through efficient binary protocol that is proprietary. And then we used an Eagle server as a connection server that exposes an HTTP services and then connects to the bus, and then this is how we are getting HTTP requests into the system. So this is how ad serving works. This is only the real-time bidding process. There are other back channels that are used to between the components to notify on any corrections that need to be made when something when there is an error. So if something needs to be reverted back or updated, there are other back channels involved in communication. What we need in ad serving is high availability. We cannot have downtime because at these speeds there are large ad exchanges. They can handle tens of billions of ad requests each day, and any downtime is a big money loss. There is also need for correctness and exactly once delivery, because if we have broken somewhere in the message flow and we have a winning bid, but we don't do anything with it, we don't serve the ad impression, then the advertiser is getting charged, as Colin mentioned. And if we have duplicate messages, if one message is handled multiple times, it's possible that we then have initiated a bidding process several times, and someone is being charged for impression that wasn't served. So After having worked with the X platform in ad serving, how these previous problems, how they fare with the X platform. So to the one of the main strengths for us was ease of development, because we only think about the business logic. Colin demonstrated how the micro app looks, how the code looks. There is only handling incoming message, dealing with your business logic, and then updating the state. And the state is like just a regular Java container structure. So we mutate the state and then we send something out, and that would be it. The concurrency model is built in. It's very easy to scale. It's mostly done through smart routing of the message. So the way you organize, you simply partition the state and then route messages in a way that will enable you concurrency. And also a very simple, from that comes a very simple horizontal scaling. One of the main strengths for us is the in-memory storage, and also persistence that is enabled simply by configuration, not by coding. So the application itself is persistence ignorant. It doesn't need to do anything after we have updated this Java container structure in the state. We basically did everything we need to do. There is no remote caches. There are no cache misses. The state is in the memory of the process that is executing the business logic, and there is really no delays in accessing the cache, and there are no issues with initial loading, populating, and so on. There are no issues with garbage collection. X Platform provided the model for zero garbage. If we follow certain conventions, we can avoid garbage collection pauses. It's so from all that comes it's easier to set up for development. It's mostly about just pulling down a Maven project and building it, and we can try everything with few commands. We can also try a lot with just writing up unit tests. So it's easy to do integration testing. It's simplified for IT. For small businesses, it's really difficult to start out a small project and then deal with all the configurations and deployments at the start. Small businesses really need to try the business logic first and see if the project is a viable one, if it's something that can succeed, and not deal with everything else regarding the way to set it up and how to host it and everything else. And we need to do it on cheaper commodity hardware, at least at the start. So from all that comes really comes increased productivity. We only are concerning ourselves with business logic, and we only deal with a very small amount of setup and configuration. So I would like to demonstrate how it looks how it looks to manage an X Platform application. So this is Luminum server. It's a great tool for introspection into running X application system, and also there is a way to deploy easily applications through this to a cluster of machines. There is a service called Robin server, and which has a certain packaging format for X Platform applications, and we would basically just wrap the application and then upload it to Robin server and then run it. So here we have an ad serving system. We have run some warm up to test that everything is working in order, and I can I can run a simulation of, say, let's send 100,000 add requests, and let's do it in a rate of 1,000 per second. Okay, so we have started with 10,000 messages, and at the end of the run, we should see 110,000. There should be no loss since it's a guaranteed delivery. So we can see now the times the average goes to up to 1.5 to 107 milliseconds. It's dropping down now. So at 1,000 frames, 1,000 requests per second, we are every time on every request we are bidding with 1,000 campaigns. So at this rate we have around 1.5 millisecond average. And if you look at here, these are the actual processing times inside the micro apps. So we have some small overhead due to our lab setup, the messaging layer that we use. If you look at this, the largest time is spent on actually just searching for campaigns, which is algorithmically the most complex. All other handlings are in microseconds and way below in microseconds. So we see that we can get some estimate on what we need to scale. We are running this on basically on 3 machines, this system. So what we can try now is to test the guaranteed delivery even more. Let's say that let's run the same benchmark. We have one of the applications we are running replicas and the ad exchange, which is the most contended place in the message flow. So let's say that we try to kill this node. So the replica should just keep working, but there should be a failover to any messages that went to the killed instance. They should still be redelivered to the backup, and when we add up at the end, since we started with 110,000, now we should have 210,000. And okay, so we can see that the failover caused some delay. The X platform advertises up to a second for failover, so it's possible that we had to discard some of the ad requests because they didn't meet the required delivery time. But still, since there is guaranteed delivery, we won't have any actual message drops due to failover, so we can easily use these even messages that have expired. We can still use them to easily make a corrective action to any bids that occurred. And in this case, we actually didn't have to do even that because everything was still handled. So all of the ad requests were served with ad responses in good time. So that would be it for demo.